So welcome you on today's session, mainly on linguistic summaries. It will consist of four presentations. Out of these, three are co-authored with Katarzyna Kaczmarek-Mayer. And the first lecture will be entitled Measuring the Temporal Stability of Fuzzy Linguistic Summaries about time series with drifts, and it will be given by Marcin. So take the floor.
Hello, everyone. My name is Marcin Ostrowski. I'm with the Systems Research Institute of the Polish Academy of Sciences. And today I'd like to present some of our most recent work in a presentation titled Measuring the Temporal Stability of Fuzzy Linguistic Summaries about time series with drifts. So let me... These two are not working. No, still no. No. The pointer is working, but the slides are not changing.
Maybe batteries are okay, but maybe you are not in the correct screen. Yeah. Right.
Use mouse to get to the
Yes.
presentation and then.
Okay, so I'll just point.
Let's try. Nothing.
Oh, wait a minute. No, still no.
Still not.
No,
No.
no, nothing. No. Okay, maybe mouse manual.
No, nie? Zobacz, pójdę,
Is the pointer on?
Yes, the pointer is working, but I cannot change slides. That's the problem.
Try to switch off and switch on.
We did already, but maybe
And translate the out and back.
So
Musi to fungować manualnie. No.
is this one from the pointer?
Oh.
Can try to.
Oh yeah.
No?
No,
No.
no.
Maybe.
I'll try to maybe open.
A to druga okno.
Nope.
I to? Okno.
Okay.
No, predatora ci przed.
So it's not working. Okay, thank you. Oh, right. So after those small technical issues, let me begin with motivations behind this work. While explainable AI has made great progress in recent years, the dynamics of explanations in time-dependent settings remain largely unexplored. Most explanation methods overlook how explanations evolve over time. Yet this evolution might be extremely informative. Fluctuations in explanations might yield information, valuable information about models' behavior, data drift, or even redundant use of features. Understanding those fluctuations might lead to creating models that are not only explainable, but also more trustworthy and stable over time. Most existing explanation methods treat time points independently without considering how explanation change. A few recent approaches have started to address this. However, these approaches, their primarily focus is to produce smooth explanations rather than quantify their stability or consistency. This is the gap that we aim to address rather than proposing yet another modified explanation method, we propose an index which quantifies how explanations change or remain consistent over time. Formally speaking, we consider a multivariate time series with k features and t time points, and great, now the pointer is not working really good. Okay, let f be a real-valued temporal process, which represents evolution of explanatory quantities over discrete time points, and each value f t summarizes the explanatory information available up until at time t based on information available up until time t, for example, via aggregation over a batch of observations. The goal is to quantify deviations of explanatory signals from their expected temporal behavior. But first, before we assess whether explanations behave as expected over time, we need a notion of what expected temporal behavior means. Here, we construct a one-step reference trajectory, f with a hat, of explanatory signal ft based on past values. To do that, we use a modified exponentially weighted moving average, or EMMA for short. The first two terms correspond to the standard smooth EMMA smoothing, making it possible to apply higher weights to most recent past values. The third term introduces a simple drift correction based on smoothed estimate of step-to-step changes in explanatory signal. What is important that to compute all of these components, we use information available only up until time t-1, so there's no information leakage. And to ensure that we can compare those deviations across different features, which might have different scales, we normalize them using a robust scale estimate based on median absolute deviation. And with those residuals defined as in the previous slide, we can now introduce a single scalar measure that summarizes how temporally consistent explanation signal is. And this index, summarization consistency index, or SCI for short, aggregates normalized deviations from expected behavior across time points. Conceptually, it answers the question, how much does explanation deviate on average from what we would expect based on its recent history? At each time point, we transform those residuals by a loss function, bounded loss function L, which can be seen in the middle of the screen. And by default, we use uniform weights. However, due to the formulation of this index, we can naturally exchange them for non-uniform weights or for adaptive weights. And this is especially for situations where the deviations might be caused by problems with models themselves. So maybe because their performance is worse in some of the time step and the deviations occur there. In our current implementation, we rely on fuzzy linguistic summaries, which express global feature attributions using human readable statements that consists of fuzzy linguistic quantifiers, qualifiers, and summarizers. Each of the fuzzy linguistic summary can be evaluated by its degree of truth and degree of support, yielding temporal sequences that capture how validity and relevance of summaries evolve over time. As a complementary explanation form, we use Shapley values that quantify feature attributions by importances by attributing each feature's marginal contribution averaged over all possible feature collisions. And to quickly, I just want to check how much time I have left.
It's 10:50, so it's still 5 minutes to go, and then
Okay,
5 minutes for discussion.
Okay, so I will very quickly go through experimental setup. We use XGBoost models. That's mainly for the second experiment I'm going to talk about. And for the first experiment, which is based on fuzzy linguistic summaries, we use a degree of truth calculated for each summary at a consecutive time steps and degree of support as weights. For Shapley-based experiment, we use aggregated Shapley values per feature per time step using the mean, which gives us a single explanatory value at each time step. For weights, we use model performance, specifically area under receiver operator curve. Here we can see the first of our experiments, the simulated time series, which consists of 4 different segments with 4 different distributions. The first segment representing the stable, somehow stable regime from a sinusoidal function. And then at 3 time points, denoted by the dashed red line, we can see that in the first one, we introduce a change in mean. In the second one, gradual shift in mean. And in the third one, we increased the variance. The goal of this simulated data is to study our approach on data that we know where the ground truths of changes are and how they align with what we will find using our framework. Here we can see the first results. For the fuzzy linguistic summary, around half of observations have X1 feature low and X2 low. What you can see at the top of this slide is a control chart created for those summaries and quantify around half. And at the bottom, you can see the delta STI. So it's the first difference of this index we proposed. And the first difference is, in this sense, more informative, that it can be seen that for each time step, how those time steps contribute to instability, general instability of explanatory signal sequence. And another key takeaway is that mostly those peaks in our method align with peaks in control chart. The one important takeaway here is that those peaks that are not aligning with changes in regime are appearing due to not to the okay, they are appearing because of the problem, not a problem, but we use a fixed membership function. So due to the fixed membership function, we had those peaks even in the same segments. And here we can see the same experiment for majority quantifier, and once again, those peaks on our graph are aligning with, roughly aligning with those on the control chart. And here, just to very briefly go through the second experiment, we extended the simulated time series, and we did a sort of repeating stable and unstable regimes. The stable regimes are the same for every second window, but the unstable regimes, those from the first experiment, they repeat every third window. And for this extended experiment, we used Shapley values and created this plot using Shapley values for each time for each window we considered. Each window considered of two segments, and reported box plots for the unstable class. And what you can see, we expected that those will be inconsistent due to the fact that those unstable regimes are chaotic in a way themselves. But we can see that for the last about five time steps, the consistency starts to show, of course, except those two time steps. That's because those four box plots are more or less similar to themselves. And to conclude, we proposed an index to evaluate the temporal consistency explanations. The method combines the performance-weighted consistency index applied to fuzzy linguistic summaries and Shapley-based values. Preliminary results on simulated time series show that reliable interpretation requires not just importance magnitude, but also temporal consistency. And finally, future work will include extending to another attribution methods, evaluating robustness under distribution shifts, and using real-world data, and releasing an open source toolkit. Thank you very much.
Are there any questions?
Can you show the picture with time series? Yes, this one. How can you identify these changes where they are colorful blue and white, blue and yellow? Yes. So how can you identify them in the time series where they are?
Those
Yes,
changes.
yes.
So right now, this is a time series that we created, and the how to put it, the idea of the experiment was not to, in a way, show where they are, those changes, but to see how this consistency behaves in a chaotic, because this is a non-repeating, non-strictly repeating time series. We wanted to see whether the consistency, how behaves for such a chaotic time series. We could try to identify to in some way relate those changes in explanations to those changes, but this is, I think, for the further way. Another use that we find is to identify segments, and this might be in some way answer to your question, that if we have a series of explanations. If we have a series of explanations for some using some data to create those explanations, right? And we can see that those explanations are consistent over the time, but in some segments there are inconsistencies flagged by peaks like this. We can then audit further those segments to see why those inconsistencies appeared. So that might be a way to identify those other segments.
So it means that you begin with the knowledge what these segments are, and then you somehow evaluate them. Yes.
Yes.
Yeah. Only a remark, it should be, or it is worth mentioning that linguistic summary is in fact application of the theory of quantifiers, generalized quantifiers, which is the theory which does exist already for 40, 50 years.
Yes,
Thank you.
Thank you. Thank you for the discussion and presentation. And now I ask Kasia Miś to give the presentation. Is not yet there anymore, so okay, microphone plugged in. And the presentation is entitled qualitative criteria for fuzzy linguistic summaries with absolute linguistic. Take the floor.
Thank you for the introduction. Yes, this. Okay, thank you. So today I will speak about fuzzy linguistic summaries, but I will focus on some absolute linguistic expression, as you can see here, not only on absolute quantifiers, but any expressions that can be given in such a sentence. So my goals for this presentation is to briefly recall what fuzzy linguistic summaries are and show the criteria which can we use to assess them. And as I said, I will focus on this fuzzy linguistic summaries where we have absolute expressions, and I will describe their properties. Actually, I will focus on one of them. So as you can see here, we have such a sentence: about 50 employees earn low salary and have small experience. And as you can see here, we have absolute linguistic quantifier. And we may ask if this is really useful to use such absolute expressions. Maybe in instances like here, we can say they are not so common to use, like, or maybe like this one. Again, maybe not always we use sentences like here where we have employees that are about 30 years old. But in some practical medical applications, we have such sentences, and I'm sure that any of us who did some blood test, we saw that we have some results where we had some absolute expressions if some level is below or upper some number. So, for example, we can have such a sentence: about 100 patients with high blood pressure have a pulse around 90 and the blood sugar level much higher than 120. So this is very, I think, a simple example, but to show that in many areas of medical applications, we may find such sentences. Of course, we can have the following sentence, like majority patients with the same attributes. So as you can see, in such a sentence, we don't have an absolute linguistic quantifiers, but the relative one, but still we have some absolute expressions in the role of summarizer. So to briefly recall what we call the fuzzy linguistic summary, to define this, we will need some notations. So we have a set of objects, we have a set of attributes. So in the case of the last example, these attributes could be the pulse, the level of the pulse, and the number, the level of blood sugar, for example. We have also sets of linguistic expressions for each attributes. So if we consider some relative expressions that will be low, high, and so on. For absolute, there will be below some number and maybe between two numbers and so on. And also we define the following family V. This is a family of fuzzy sets. And each fuzzy set which is in this sense, in this set, in this family, expresses how we understand some linguistic expressions for example, low, high, and so on. So the fuzzy linguistic summary will be such a quintuple where we have a set of attributes A, we have a set of linguistic expressions, as I said, and we also have a family of summarizer and a family of qualifiers, which satisfies the following condition. This condition means that if any fuzzy set is a summarizer, then any other expression that describe the same attribute, they cannot be they cannot be in a role of qualifiers. So we cannot have a sentence like almost all young employees are old, for example, because it doesn't have sense. And also we have, as we can see here, a linguistic quantifier, and we have some aggregation functions, star and diamond, and they express the logical, the connectives that we have in such a sentence, because we can have and or we can have or, so these functions can be disjunctive or conjunctive. So this is the fuzzy linguistic summary. This is how we understand that. And if we have here some connectives, again, they can be translated into, as I said, into some aggregation functions. So this is how we can aggregate the values of all qualifiers and values of all summarizers. So the question, which is, I think, more important for today for us, is how we can evaluate such fuzzy linguistic summaries. And there are many such criteria. There is a degree of true, degree of imprecision, of specificity, degree of focus, the degree of support that Marcin said about. We have a degree of fuzziness, and so on. So there are many different such criteria that can be used. Today I will focus on the first three, so the degree of true, degree of imprecision, and the degree of specificity. For some number j, we can define such a family of criteria, and for today I will have such three criteria, as I said. And the first one is the degree of true, which is the basic one, we can say the most important. And we have the definition of this. As you can see here, there are a little bit different formulas depending if we have relative or absolute quantifiers. And in both cases, we have some conjunctive aggregation functions that we can say connect the values of summarizers and of qualifiers that we have in our sentence. Another degree is the degree of imprecision. In general, we can define the degree of imprecision of any fuzzy set by such a formula where we have a measure of such a set where the values of such a set of such a fuzzy set are positive, and here is our universe. And me can be some measure. Usually, if we have a finite set X, we have that me is a counting measure. If X is such a interval, then me would be the Lebesgue measure. And if we for the degree of imprecision of our linguistic summary, as we know, in such a summary can have more than one summarizers. So this is how we calculate the imprecision of summarizer. We use here a geometrical mean. And then we can have the value of such a criteria, of such a degree of imprecision for fuzzy linguistic summary it is such a number. As you can see here, we have some numbers which are W, R, P, and Q, which are positive, non-negative, and they sum up to 1. So this is how we evaluate the degree of imprecision. And another one is the degree of specificity. First of all, we have a definition of measure of specificity for any fuzzy set. So this is a function which satisfies this condition. So its value is equal to 1 only if A is such a set. So it is just a crisp set, and for a empty set is equal to 1. And this function is increasing with respect to the number A1, which is the greatest, the largest membership grade in such a set A, and it is decreasing with respect to some other AJ. So we can say that the specificity of the measure of specificity of fuzzy set is the greatest if we have just the crisp set. So it measure how we can say our set crisp is. We could say something like that. And there we have some formulas for such a specificity for fuzzy set, which were proposed by Jager. For a finite set, we have the following one, where we have this integral, and here we have A alpha, which is the alpha level set of our set alpha of our set A. And if we have that X is such a continuous domain as an interval, then we have that the specificity is given by such an integral where f is a decreasing function, and our measure is Lebesgue measure usually. So having this, the degree of specificity of fuzzy linguistic summary is given by such a formula. So as you can see, very similar to the degree of imprecision. And now the property that I would like to check today and check if this property will be satisfied for our criteria. So because I mentioned about some absolute quantifiers, I will say about some antonym quantifiers. If we have the absolute quantifier, then the antonym quantifier for this one will be defined in the following way, where n is a number of object which is in our set Y. And now we can say that the antonym property is satisfied if for some criterion T, if the value of this criterion for the fuzzy linguistic summary is the same as for such negation form. As we can see, the negation form here is given by is given in a way where we have antonym quantifier, and we have some negations of summarizers, and also we have a different operator here. This is a dual operator, so if we have and, the dual will be or, for or, the dual operator will be and. So for a very simple example, about 10 employees low salary, such a negation form would look like this. About n minus 10 employees earn not low salary. So this is how it looks like. We checked those. We checked this property for this criteria for some sentences, and as you can see here, I have some sentences which are quite simple, I would say. For all of them, as you can see, this criterion of this property is satisfied for the degree of true. If we have this, the first sentence and the second one, so again, this is a simple one, but here we have an absolute quantifier, and here we have an absolute expression for our summarizer. However, for a more complex summary, like here about 100 patients with high blood pressure have a pulse of around 90, the degree of true can be satisfied. This property can be satisfied for this degree, but it doesn't have to be. As you can see here, this sentence is more complex because we have here a qualifier that we didn't have before. And we have a simple result which shows us when this property is satisfied. So if we don't have any qualifiers, then this property is satisfied for the degree of true in general. However, if we have at least one such qualifiers, then this property is satisfied if this function C, which comes from the formula for the degree of true, I showed you there was a conjunctive function there. If this function satisfies this functional equation, and If we think about maybe t-norms which satisfy this equation, so among only continuous t-norms, there is just one such function, which is a product t-norm. So we need to have the following assumption. And going back to other degrees, in general, they are not satisfied, as you can see, because this property is not satisfied for this degree, is because they are defined in a different way. So actually, we may say that this property will be satisfied depending on the particular sentence, depending on how this fuzzy set would look like. So, for example, if we have this sentence, the degree of true will be only depend on those summarizers, how they look like. So, as you can see, in this case, the negation of such a summarizer and the degree of imprecision for this one would be the same, but the degree of imprecision for this around 90 summarizer is completely different, because as you can see here, this interval red is bigger than the blue one here. So it is not satisfied. Also, we have another remark, which are part of our future work for such sentences. So you can see here we had such sentence with a connective and we can have the following sentence with connective, the same sentence but with connective or, and we can say this is, in our perception, this sentence is more imprecise. However, in the definition of the degree of imprecision, we didn't have any distinction. There was no differences for different operators. So our idea is to extend this and maybe to make it more general, to make this degree more general, and to use different operators for defining the degree of imprecision of summarizer. Because as you remember, there we have geometrical mean, but we can use any other quasi-arithmetic mean, and we know that quasi-arithmetic mean can be comparable between themselves because of the convexity of such a generator here. Okay, so I will go till the end. And also, I didn't mention about the degree of specificity. And again, in this degree of specificity, we don't have any differences because of those operators. So what we would like to maybe to extend it is to put here some aggregation operators to make the difference between such sentences where we have and where we have or. So that was, and as I said, this is a part of our future work. So this is what we would like to do with these degrees, and also to compare relative and absolute expressions. As I said, in medical applications, which they are where there are really important. So that's all. There are some references, and thank you for your attention.
Thank you for the presentation. Are there any questions?
In your slide, you have a table, and you write that degree of specificity, or no, this one, yes. What does it mean? The degree of imprecision is satisfied, or degree of specificity is satisfied?
Yes. It means that not the degree, but the property of the antonym property is satisfied for this degree, for this criterion. That the value of, like here we had that the value of degree of true for such a sentence is the same as for this antonym version. But in these cases, if we take antonym versions of such sentence, then the degree of imprecision has different value in general.
And why?
Uh, well, I'm not saying it's bad. Well,
Or why you need to be equal?
Because well, in our perception, sometimes such sentence, if we have these two forms, some people can say, I don't want to say that they have the same meaning, but yeah, but in some sense, well, they should be in equal of well, the two of them should be equal, maybe. But you're right that they don't have, that they don't have to be, right? It's not the principle.
Well, thank you once
Okay.
more.
Thank you.
And now to the third presentation, which will be indeed a share presentation of Kasia and myself. We will switch somewhere in the middle. And
Okay,
so it will be the kind of experiment. And the title of the presentation is on the dissimilarity of fuzzy information granules.
Okay, good morning, everyone. Thank you, Martina, very much for the introduction. So let's now dive directly to the world of granular computing, just to briefly recall the definition. So at the formal, well, abstract level, as introduced by Professor Pedrich and in the recent years intensively explored, an information granule is some formal abstraction that collects basic elements into a higher level unit according to the granulation relation that reflects similarity or some indistinguishability under a given criterion. And at this abstract level, this definitions we see, though quite general, from the very roots, it was the aim. Then we may, in a mathematical way, then denote the G as a granule. We have E as a set of elements and R as this relation that expresses some granulation criteria. In practice, this may be similarity. There are various approaches, clustering, memberships. So that's important. And now within each approach, there are some metrics that enable us to assess the quality of a given information granulation approach. However, what came to our mind last year, and we started to seek solution, was to answer the question whether and how we can compare or assess the similarity, or in the end, the similarity at this stage, between granules generated for the same E, the same data set, but in some different approach. And this evaluation seems to be challenging part, even for a particular specific approach. And to somehow limit ourselves, as we already realize, it's a very complex task, and that's in fact we will be really happy to discuss today whether how to even attempt the assessment of this similarity between granules generated with different approaches. So let's consider this example. This is an example of fuzzy linguistic summary. And then for another information granule that we may arrive at could be the fuzzy association rule. My colleague will be talking much more about that. So then we did with colleagues from Ostrava and some psychiatrists, we did experiment last year when we generated for the very same data set those different granules, so linguistic summaries and association rules. And at the same time, we also ask doctors to assess first the original data, but also we ask them feedback about those information granules. And the results we got were very, well, we found them really encouraging and interesting, saying that, well, first of all, the doctors were very good based on the voice to analyze the mental states, but also then when it came to explanations considered as information granules, so first of all, it confirmed that they found them useful. At the same time, when asking them whether they have preference for rules or linguistic summaries, a slightly higher satisfaction was perceived with rules, which still, this was a pilot study. We considered 12 doctors and in total over 100 samples. We want to repeat this as a bigger study soon as well. At the same time, what is still an open problem was that still in the explanations that we provided, experts found not enough information. And then on our side, we realized what was the problem was the selection of the top information granules that we may present to them. So this is the challenging part, to really select only those that on one hand are very informative, and on the other hand, they do not overlap. So therefore we aim at searching for approaches also to compare different ones. So now coming back to the more specific, now in the fuzzy setting, we will consider this G as granule, and we have a universe and that defines a mapping and a gamma function that reflects this evaluation criteria. And we will focus on how, namely, to assess the similarity of pairs of such granules that come from different approaches. And now, okay, the definition of the fuzzy linguistic summary, we are following the approach initiated by Jager and recently also developed with colleagues from Poland. So I will skip this definition, as Kasia and Marcin already mentioned them. And in this particular approach, we also focus these two measures to assess the quality of linguistic summarization. And then for the selection of the top information granules to be presented to the final evaluation, we consider a simple algorithm where we try to, on one hand, to select those that maximize, of course, the considered criteria, but also we want to have them on one hand complex, and in the future, ideally, we will here try to integrate them, trying to search for those that are not similar to each other. And yes, so we select those top ones. Okay, so this switch. Now we switch.
Okay, so thank you for the nice introduction. And now we switch to fuzzy association rule. So how it differs from the previous approach? Well, it generates the rules based on the optimal pruning on fuzzy support, considering fuzzy support and fuzzy confidence. And additionally, afterwards, it computes the Guha-based quantifiers, or let's say, in other words, hypothesis-based quantifier. In our case, so the special study, we used the Lukasiewicz-based implication. So we measure somehow the positive samples and negative samples on the basis of implication in between. So afterwards, we use some post-processing things that filter out the rules that would make a confusion to the real psychologist evaluation. And we employ also implementation provided by Michal Burda. So in this implementation, it effectively extracts fuzzy rules, which are pairs of antecedents and consequence. And of course, it can generate a long vector of characteristics together with those couples of antecedents and consequence. What is the main task that we and question that we pose? So how to evaluate the difference between those in several cases very different, no, maybe not very different, but different summaries we obtained. And this is caused by the application of different algorithms, different post-processing, and also the different characteristics used to evaluate those generated rules. So our thoughts were mainly to compare these output meaningfully, it has to go beyond the symbolic overlap of linguistic expressions. This is clear. But, and we were thinking to incorporate the quality measures for the quantifiers or qualitative measures, and to reflect the semantics, which means behavioral difference on the models level. And of course, what is listed the last, but it's mainly important is to remain interpretable and monotonic in some certain sense. So for simplicity, I just rewrite the fuzzy linguistic summary and as well as association rules in this simple form where the first upper letter means the rule. So it's the strings containing antecedents and consequence. And this, with small letters, these are the qualitative measures. It can't be of the different lengths. So the vectors of qualitative measures in the first case could have m values, and in the second one, and even more numbers. So in the first case, these are degrees of true and degree of support. In the second case, Q is the implication quantifier, a Guha-based quantifier, and SJ is the support. So both collections can be treated as individuated set of information granules. Well, we were thinking about the splitting the job into some sub-cases that are relevant for first to structural dissimilarity measure. So either as one case, we can just sum up those elements that are different in both linguistic expressions. So for example, in our case, we have generated 2 linguistic summaries of that form and 1 fuzzy association rule of that form. We took a look on linguistic expressions inside, like for example, low voice energy, and just count out simply whether it repeats in one set of linguistic expressions and into another. And in this case, we obtain 1 because there is only 1 linguistic expressions that is different in both sets. Well, this is not well, really nice. Sometimes we are preferring to have it normalized. So for this case, we can use, for example, Jacob distance that takes the ratio of the intersection with the union of the numbers of linguistic expressions. So in this case, we are now in the interval 0, 1. And for this very simple example, we obtain the degree 1/3 for the dissimilarity of these 2 linguistic descriptions. So on that level, we are happy to have a purely symbolic nature of the measure. And well, there is an absence of weighting. In this case, we have normalization, but we are missing semantic proximity. So this might be the one block of the general measure of dissimilarity. Another block might consist of semantic measure that take a look to the model of the linguistic summaries that we have at disposal. And for example, we can take the measure of subsethood of one function or a fuzzy relation for the model within another. And let's make it symmetric. So we measure the subsethood of one model in another and another in the first one, and we just aggregate and take the 1 minus of this value, and we obtain somehow a measure of this similarity on the semantic level. Well, we can think of more sophisticated approaches. We can compute it by means of integral of the absolute value of the difference of the models or some other. So this might be the second block, and in our case, we would compute the following value. So the dissimilarity on the semantic level is half. And indeed, it is challenging to go to the last block where we consider the difference between the qualitative measures. The problem is we cannot just take the integration over those values because they are very much different with very much different interpretation. So either we focus on the intersection of the qualifiers or we take the completely different approach. But our main idea is to aggregate all those segments into the single one to receive the one single value that evaluates the difference between our two linguistic summaries, let's say. And it will be indeed our future work. So we will analyze the proposed dissimilarity measures, so mainly whether it is monotone, and aggregate these sub-parts, so in our case, the structural, semantical, as well as qualitative, and propose a measure, mainly the measure on quantifiers, and integrate, of course, the gold rule, the expert provided linguistic description. So we can compare our generated rules, but the best is the expert, let's say. Not always, but we should at least incorporate as its golden rule. So there is only maybe the last comment that there are several works on that topic, and well, the first one investigated association rule measures and use it for compare their predictive behavior. Also, the Dudek, the guy from Poland, he used these measures. Indeed, he used support and confidence to compare rules based on the rule overlapping. And the third work, well, it focused on the very ground level, only the comparing the membership functions of linguistic expressions, and they use them to simplify and merge a fuzzy rule basis. So, job in front of us, a lot of literature to explore, and we would be very happy if you could give us some nice hints. So thank you for your attention. The lists of and maybe this is again turn to you, Kasia, to make some advertisement for summer school that will take place in Warsaw. We have
here.
1 minute.
So
Yeah.
together with Professor Przemek Grzegorewski and the Polish Society for FSTA, we will be organizing the summit school in July. So it's well, details about the speakers would be available soon. But for sure, if you have options for the doctoral students, we really kindly invite you. We will try to make it inspiring for the young researchers.
So thank you. And now is the floor for one question or comment, if you have any. I think it's too short. Yes.
Surprise, I have two comments. Semantic measure.
Mhm.
You take an average which does not fit the logic framework, you could use an AT norm or use the residuation inside.
Yes,
and
yes.
Still guarantee the transmittivity
Mhm.
as complementary, so use a lot.
Yes, yes. There are very many possibilities to aggregate those two subset groups indeed.
My general question applies to all of them. We have all these tools around nowadays, large language models and like BERT. How would they embed the text or a summary of yours into some high dimensional space when you generate an embedding vector? You can compute similarity there. How would these align? I'm not saying that they are perfect, but it would be curious to see to what extent do these language models capture actually. Okay, so maybe I'll ask.
We had tried there in some experiment, but well, we didn't found them yet like full, well, inspiring outcomes. But here, in fact, we consider a different problem, which is data to text, and also mainly for confidentiality, at least with our data, we were not allowed at least to support. So this was one limitation. And to tell the, well, I'm not sure what are in this context, like to data to text, not sure about the quality of metrics that large language models. So still we believe in math and so we, at least this way, we believe it's not done yet there, but
I would
Well-
warn you.
Well, indeed, I tried, yes, but it doesn't want to generate a single value as a degree, but it gives very long text, just listing the differences in between. Yeah. So another thing to evaluate.
We tried.
Uh-huh.
The language, map it to the space, and then say, did this problem occur before? Not exactly, but using the similarity measure in the embedding space, we can retrieve confidence that experts say that are very similar or interesting to learn that they have recurring failure and so on. So these measures have some value.
but okay, so you would recommend these measures? Just
Sorry, as the chairman, I would need to shift this discussion to the coffee break or the lunch and give the space to the last speaker. Will be on linguistic summaries in weights, adjustments, and criteria reduction for evaluation and multi-criteria decision making.
Thank you for the introduction. My slide disappeared. Oh, thank you. To keep the continuity from the previous talks, we used the same template with the same color hues, or at least. Introduction was already told. Presentation roadmap is that this was a work in progress and some kind of idea how when we have conjunction, main conjunction, but also averaging evaluation, then we have initial weight assignment, and then the question is how to modify and adjust the weights. And finally, I will focus on our future more ideas and concluding messages. So when we look at the conjunction, quite interesting topic. The number of elementary condition increases. We know that probability of anti-assign problem might appear, and also it is not an easy task to assign weights of all of them. The same holds also for averaging another evaluation. We have a higher number of elementary conditions. And although there are two questions. Firstly, are all of them really necessary of these elementary conditions? And second one, how to modify weights, but also considering dependencies on asymmetry influencing of one criteria to other or the opposite case. So a little bit about initial weight assignments. Let's say expert on someone assign weights, but when you have conjunction, in this case, we have a different way for weight assignment because all elementary conditions are mandatory. And option is by implication. We have several implications. For instance, it is a in this implication, when we see when weight is, let's say, 0, then due to neutral elements, elementary condition does not influence the solution. In the opposite case, when weight is 1, even a very small value of elementary condition fully influence the solution. In other cases, as averaging evaluation, simple additive score, simply multiplicative scores, utility functions, sum of weight should be equal to 1. In the previous case, it is not the case. In the previous example, is not the case. Okay, so how to assign a future weight? Because usually experts assign initial weights, but some hidden dependency in data, etc., might influence such. Then, and usually we have options like critic. It is method modified intensity weights by correlation measure. That is very nice. But from the interpretability for user might be a little bit problematic. And also the question is in correlation is symmetric measure, whether whether let's say criterion A influence criterion B more or the opposite, when you would like to reduce weights of remove criteria. Okay. So our question was, should we adopt linguistic summaries in this case? So let's say if you see most of small changes in criterion A, have small changes in criterion B, or the opposite. And in that case, first of all, we need to should normalize numerical criteria to make sense for such kind of summarizations, but it is no problem in many data mining and other tasks. Normalization is a usual preparation step. Oh, I forgot to check my, okay. So we see that it is not the symmetric. So small changes of A and small changes of B is not the same when small changes of B cause small changes of A. And also could be benefits that in small imprecision of data, or let's say someone put several wrong data, that could be mitigated because we are not in a sharp statistical way, let's say in Spearman we rank values, and these small changes may cause shuffling of the data. Okay, so the first part, this is idea is presented in the following way. When you have it will work, criterion A, criterion B, and we calculate differences in values between all possible pairs of alternatives. And then we came to the difference. The difference is between 0 and 1 because we are normalized. And then we have fuzzy sets, let's say small, which has small presented as a decreasing functions, and then also quantified most often. And computing the validity of linguistic summaries is well-known equations. I will not go explain it because we noticed this equation several times during the previous slide, but say that the conjunction should be by idempotent T norm, otherwise we have downward reinforcement issues. The other measures of quality I'm going to tell you by the end of the presentations. And now we came to the heat table compared to correlations, but this heat matrix is a little bit different because we have criteria, then clearly on the diagonal is 1, but C1, 2, and C2, 1 usually are not the same. So between them, difference exists. Okay? And you have such an idea. You need requirements for adjusting weights. So if, let's say, criterion A is more influenced by other than influences the others, weight should be reduced. In the opposite case, when the criterion more influence other than is influenced from the other or something like that, then weight should be increased. But in conjunctive situations, if R is equal to 1, doing nothing. The third one is related to usual way if of weight adjustment by correlations. If let's say more or less equally is influenced, I influences others. In that case, is this value is very low. Weight of both of them should be, let's say, emphasized. Is if it is very high, reduced, and it is in the medium, let's say, keep the same. Okay, and then now we proceed with the calculations. We see that plus means a better way influence other, minus means influenced by the other, and then we simply calculate arithmetic mean by excluding self-influence, which is always the one. Arithmetic mean because from logical point of view it is the only neutral logic aggregation functions, and then we compute both values which are already in 0-1 interval. So this is some also idea, but we can use many other functions, just idea how it might work. So the difference between influencing other is influence is in our case is theoretically between -1 and 1. So we see weights is reduced when this difference is quite, let's say, very negative. Weight is reduced, but in theoretically, if they be -1, weight will be 0, and we see that is neutral element for conjunctions. In the opposite case, we improve weights by using value d of the difference and divided with total number of criteria to not increase significantly. The interesting case is when you have a very small difference, then the weights modify by parameter A, and this parameter A could be represented in the following way. That's simple, because z plus and z minus are very similar. Then we see that we take ether max of arithmetic mean is not so issues, and let's say some kind of this kind of functions, which could be, let's say, modified, etc. We see that if a difference is if z's are very, very low, that both of them that we improve weights. If they are very, very high, then we decrease weights, and they are in the middle, let's say, we keep value almost the same. Okay, and then let's see, in this case, in fact, we have weights adjustments which do not require for conjunction evaluation normalizations, because in this case it is not the requirement. Okay, the next question is excluding significantly influence criteria. It is the task how to remove them, especially when you have a larger number of elementary criteria. In this case, this is just idea, because generally it is inspired when you looking even on your watch, I say 0, nothing, 0.25 light, 0.5 more or less, and 0.75 very high. In this case, the difference multiplied by m, where m is like in text mining when we have dumping functions to reduce, to influence, so if distance is very low, and then if value m is relatively high, in that case we could remove less relevant criteria. This is just a illustrative example when we say that 25 would be nice value, but these further experiments are really required. A little bit about these initial experiments. In the first case, we have relatively larger differences. We see this is larger in positive, so weight is improved. When this very small, first, last by one last, all of them are lightly increased because the values we see are less than 0.5. In this case, we see a significant decreasing of value. Another case, we see this case when values are very light modifications. We see in this case was significant increasing, In that case, the weight are more increased than in this case when the weight is slightly increased. Also in this case, its value is 0, but we see more than 0.5 above direction, so weight is slightly reduced. In the opposite case, weight is slightly improved. Also, initially, weight was set as one of very important, but due to negative influence of other criteria, the value is modified and put little mode down. Okay, and then when you look whether, let's say, as the illustrative example, reduction of significant influence criteria, so we see that in this case we have a relatively low value, but also when we multiply the parameter and we go beyond the 75 and say yes. But that is also interesting to say that it is not, let's say, some kind, okay, thank you very much, some kind of final solution. That is idea which could be modified, let's say, by machine learning or something like that, or proposal for user to see how data influences, because we have structure, someone said weight, and then information about influence between criteria which is not a symmetric one. Okay, so considering benefits, adjusting weight of numerical categorical data and removing maybe, let's say, no so problematic as linguistic summaries work with both data. Also, we should be also here we be careful that we have correlation which, let's say, moves to the causality, because we see direction, but still should be careful because it should be also just the case that it might hold. And we see the second role of linguistic summarization. It is that we see that we have linguistic explanation of dependencies. So someone could see, let's say, more information by correlation, especially for user not very, let's say, familiar with statistics. Then if you have a sum of weights equal to 1, clearly the next step should be normalization. But there's a lot of future work ahead. Improving functions, this is some idea how this structure might work, so a lot of work is ahead. Comparing with existing methods, mainly they are based on similarity, but it's very nice to see whether we have other options. And that's very interesting for weight for quantified queries. The third role of linguistic summaries in this case, when you have questions, majority of atomic conditions should be satisfied. So to more to merrier. So we see in this case, we have quantified query. We move from the nilpotent conjunction through the conjunction, average function, nilpotent disjunction, and nilpotent disjunction. For instance, if all of them satisfied with 0.9, we get ideal values. So this assigned weight could be, let's say, more tricky, because for conjunction we have implication, for disjunction we have co-implication, and for averaging we have a usual multiplication by weights. And then question is about computational demand, because when you compare all the pairs of attributes of entities and criteria, it can be quite demanding task, but there can other options helping for statistics which could be applied. And also, is the validity of linguistic summary sufficient measure? Clearly no. So we might add, let's say, data coverage, etc., and aggregate them by ordinal sums to keep upward and downward reinforce when we have all measures are quite high, keeping the interval 0, 1 to have our heat matrix satisfied, and also to meet the 2 minutes. So the last slide. You notice that, for instance, a few years ago, it was in article in decision support system, also by famous operational researchers Roman Slovinsky, in 60% case, a quite interesting number, improper use of multi-criteria decision method, also this is related to weight. So maybe could be a contribution in these directions, and also this is an quite hard task, as I mentioned, so we have to work in these directions. So we see that this work tries to contribute with an explainable and asymmetric model, and also this is a beginning. There's a lot of work ahead, so it will be nice to see comments, ideas, whether it is not reasonable to go future or very relevant to go future, etc. So And yeah, several main references we used in our presentation, and I think that I'm fuzzy on the time.
Oh, you're really nice. Nice. Please, are there any questions, remarks? Okay, if not, we end this session, and I wish you a nice afternoon and a good lunch. Thank you.